or today lecture, please, after this, always please enter into the class at the scheduled time. Okay, don't ask me, okay, have we any class, yes or no, or something like that. Please enter to the class always. It's regular, and by default we always have class according to the schedule. Okay, so always use always enter the class, and always use the permanent link. I prepare a permanent link for you. It's not possible for me to repeat it every day. The links are permanent, and you can use them always to enter the class. Okay. Okay. Today we will continue with we want to look inside a router. Look at the architecture of a router. Okay. If we look inside a router, we can see some special parts, but all looks is a high level view. We don't want to enter into the details of a router. Say why or couldn't design why. Oh, okay. Mohammed Hassan has a question. He asked me why queuing delay is the most important source of delay. Why? Because the rest of sources of delay, for example, processing delay, node processing delay, propagation delay, and transmission delay, those delays are fixed and narrow. I can calculate them easily, but I cannot talk about the queuing delay, because the queuing delay is dependent on the behavior of the network, the traffic behavior on the network. If the traffic is traffic level or traffic intensity is low, so the queuing delay is low too. But if the traffic is congested, we have to spend lots of time in the queue before serving. Okay, so it completely depends on the behavior of network, and we always have to care about those levels. We cannot forget them easily. And as I show you in a trace route, we start the trace route command in the class, and there is a sample in the chapter 1. You can see different delays time, different delays. It shows you why queuing delay is important. The delay is changed rapidly from one hop to another hop. Maybe sometimes it becomes high, and sometimes it becomes low. Why? Because the queue length is changed during the time. So the queuing delay is changed too. Okay? Is it enough, Mohammed Hassan? Okay. We want to look on architecture of a router. A router consists of four main elements: input ports, output ports, a routing processor, and a switch fabric. Input ports, output ports, routing processor, and switch fabric. These are four main parts in a router architecture. However, I should mention that a similar architecture we can see a similar architecture in network switches. This architecture is general, and you can see this architecture in switches too. Okay. What is the difference between a router and a switch? The differences between the router and a switch is that a router can think better than a switch, because a router has more software capabilities. Most of parts in a switch are created in hardware, but a router has too many software capabilities. So you have to configure a router, but you can use a switch directly. This is the big difference between a switch and a router, but their overall architecture is similar. Okay, their overall architecture is similar. Okay, we want to talk about this architecture. The first part is input ports. An input port consists of line termination, link layer protocol, and processing in layer 2. Line termination is the physical layer of network. It depends. For example, if I use copper cables, or if I use a fiber cable, or if I use a wireless medium, these types have different line terminations. Okay, so we can say that the physical layer functionality is gathered in the line termination section. Link layer protocols are gathered here in the link layer section, and in the red zone you can see basic functionalities of layer 3: packet lookup and address lookup, and forwarding a packet, and maybe a queuing before transferring data over the switch fabric. Please pay attention that when we talk about queuing in network, that queuing happens in the output links, not this one. The queue here in the input port, the queue just manages the passing traffic over this switch fabric. So the output of this queue wants to travel past the switch fabric, traveling across the switch fabric. Okay. However, we can say that there are two different strategies in routers. One strategy is using queues in the input ports, and the other is using queues in the output ports. Mostly we use output port strategy, but sometimes some people say that okay, you can put that queues in the input ports, something like this. Okay, here in this section we extract the destination address from the header of packet, and we look for that address in the routing table or in the forwarding table to find the output path or output port. Then we forward the packet through that output port using this switch fabric. This switch fabric is a bridge to connect an input port to an output port. But how a routing table or a forwarding table works? If I look on that on an example of a forwarding table, look at this. This is an example, a simple example from a forwarding table or a routing table. Here you can see two columns. The first one is the destination address range, and the second one is the output link we have different addresses here, and you can see those addresses are highlighted in from different areas. We will talk about these highlights. What are them? We will talk about them. Okay. But look at this. For each of those routes, we have a specific output link or output port. So, for example, if my link, my address, my destination address is 11001000101110001100 and rest of them, the output link is 3, number 3. So this packet should be forwarded to the output port 3. Okay. Maybe someone asks me, okay, for example, here the second row and the third row in this table, they are similar together. What will happen if we find more than one link, one output link for our packet? I'm searching on the forwarding table, and I'm finding that there are more than one output link. What will happen? Which of them should I select? Which of them? Here we say that we have to select the longest prefix match. It means that I should select the row or the destination address or the record that its destination address has the longest match with my destination address. I have a destination address, okay? Which of those addresses have the largest match with my case? For example, here, look on these three cases here. You can see if I look on the 21st bits, just if I look on the first 20 bits of the address, we can see that these three rows are similar together. Just look on the first 20 bits from the left to right. But you can see for the first one, the output link is 0, for the second one is 1, and for the third one, the output link is 2. But which of them? Oh, excuse me. If I look on, yes, the first one. But if I look on a star means blah, blah, blah. 0 or 1, it doesn't matter. انتصار علوي. A star means 0 or 1. It doesn't matter for us. Okay? It's not important for us. But let's have a look on the 21st bit. You can see in the first address, the bit on the 21st place is 0, and in the second and in the third rows, this bit is 1. So I can make more precise selection here based on the 21st bit. Okay, and if I look on the rest of these bits, in the second row you can see that we have three other 0 bits too, but in the third row they are stars. Here in this case you can see that the second row is a subset of the third row. The second row is a subset of the third row. But according to the longest prefix match, if I receive a packet with something like this, I should select the interface number 1. Not number 2. For example, look at here. These are 2 examples under this slide on the footer. Okay. Someone asked me, okay, what is the interface of the first one? The first one is 000101110 and blah blah. Okay, I should look on this table, and I can see that for the first case here under the table, for the first case I have choose the third row. I have choose the interface output number 2. What about the second example? In the second example, I can choose the second row or the third row. But here, if I look on the third byte of this address, I can see that the second row has the longest prefix. match. So although I can send this packet through the output port 2, I can send it. Okay, although I can send it, but because of the longest prefix match rule, I have to send it through the interface, the output interface number 1. This is the longest prefix match. I know that this address is a subset of the other one, but I don't select it. However, if I select the third row, still my packet can receive to the destination. But we choose the second row. Why we follow this strategy? We follow this strategy because if my distance to the destination, look at this, I'm standing in a point in the network. Okay? If I calculate my distance to the destination, as soon as I became closer to destination, I can find a good path with more clear details, with more matched bits. So here in this case, when I'm selecting the output link number 1 instead of number 2, instead of output port 2, I can say that this interface has the longest prefix match. It means that I'm closer through the link number 1. Through the link number 1, I'm closer to the destination. So why should I spend more time in the network? It's simple, just send a packet through the nearest path to destination. And this path has the longest prefix match. Prefix means the left bits and bytes. This is prefix. The left side bits and bytes. Okay, so look at this. Oh, excuse me. The first one should be sent through the first row here, and the second one should be sent through the second or third row. But because the second row has the longest prefix match, we choose this case. Look at this. We can choose the third row too, but we don't choose it. We don't select it. We choose the second row because it has the longest prefix. Look at this one. Here we have 21 bits matched. Okay, but here we have 24 bit match. So we selected row, the record in the row number 1. Okay, how we can use this item in reality, in a real network? We can apply this strategy using, for example, ternary content addressable memories, or TCAMs. Is a special type of memories. Just you put you enters the destination address, and it masks into the CAM, into the memory, and the TCAM memory will search for that address and will return the result. Why we say we call this memories as a content addressable memory? In a common memory, if I'm looking for something, I should prepare the address for the memory. In a common memory, okay, I should prepare the address. For example, return the contents in cell number one, cell with address 100, cell address 1010, or something else. Okay, in a common memory, just I'm saying that this is the address, and return the content at this address, or write the content on this address. But a content addressable memory is another type of memory. In this type of memory, instead of entering an address, I'm entering the content directly. Search for me on the record with, for example, something else, blah blah. Search for the record with this address, and even we can say, okay, for example, search for the record with only on the first 20 bits of the address. Only search on the 21st bit of the address. So in content addressable memory, such as TCAMs, instead of passing an address to the memory, we pass the content directly, and we ask the memory to look for that content. This type of memory is expensive because it uses a complicated hardware, and also it uses too many powers, so it's not cheap. But wherever we are looking for a higher speed solution for address lookupping, we have to use this type of memories. There is no another choice for us. We have to use TCAMs for packet lookups. For example, in Cisco Catalyst series, the Cisco uses TCAM memories. It can handle it can handle a routing table with 1 million records or 1 million entries. That is very interesting. 1 million entries. It's too many. But this memory acts very well. Okay. The next step or the next part is switch fabric. I can say that the switch fabric is a bridge connecting the input ports into the output ports. It's a bridge. This bridge, for example, let's suppose that I have n input ports and n output ports. Each of those ports have transmission rate of, for example, r bit per second. So totally, I can enter n times in r bit per second into the switch fabric. We have n different input ports. Each of them has transmission range of r. So we enters n times r packet or bit per second into the switch fabric, and the switch fabric should handle them toward the output ports. Here we say that the switching rate, a rate that packets can transfer from the input to output. Okay, what is the structure of a switch fabric? I know that the job of switch fabric is transferring data from an input port to another output port. So I can use different architecture for this. For example, in some cases, in a small routers, we can use a multi-port memory to transfer data from input to output. We are using a multi-port memory. Each output port has a specific domain of addresses. So the input ports should write on that specific domains. That's easy. But we know that this strategy is not strong. So we just use multi-port memories in just a few real cases, and it can send some. You can send a few amount of data to the output ports. Another strategy is bus. We know that there is a common bus, and the whole inputs can send their data through the output, through the using the bus into the output ports. But still, we know that the bus architecture has its limitations. Memory loss in what? In multi-port memory or in bus? Naima, memory loss where? In the switch fabrics. Yes, as I said, we divide that memory, the space of that memory, its address ranges. We divide those addresses into uh, different output ports. For example, let's suppose that I have a 1 megabit memory as a switch fabric, okay, and I have 5 different output ports. So each of them have 200 kilobit space. The volume of memory is 1 megabit, and I divided this space in between 5 different output ports. So each of them can receive a portion of 200 kilobit. If they spend all of this space, yes, why not? The data will be lost because the multi-port memory cannot handle that problem. Okay. The bus architecture has its own limitations. So when we talk about higher speed elements in computer architectures, we have to use interconnection network strategies. In this type of switch fabrics, we use a special architecture. For example, look at this case here. The first row has 3 switches on its path. For example, if the first row try to send data to the second output, look at its path, traffic comes here, and then the switch will forward it here. In other words, an interconnection network consists of too many small switches they are placing in different rows, and each row is connected to the next row, to the switches in the next row. And finally, the outputs are connected to the output ports. By this distribution, or my data can send through this architecture from one small switch to another one. In this case, we can say that this strategy is non-blocking. It means that, for example, here, if the first input wants to send data to the output port 2, another port should stop. to transfer data to our data output port. Okay, the idea of using memory as a switch fabric is very old, and in traditional computers or traditional network routers and switches, we use multi-port systems to send and receive data from one input port to another one. But as I said, this strategy cannot act very good in high speed networks because of limitation in memory. The second architecture is using bus. You can see here, but the problem is with the bus contention, because always only one sender can use the platform to send information to the output port. Cisco 5600 is using this strategy. And these are two other types of interconnection networks. You can see here the inputs are scattered through some other layers, and the result would be sent from the right side outputs. Here, as an interconnection example, you can see the multi-stage network. It's a kind of interconnection network. But here you can see a network with multiple stages. The first stage consists of 8 input ports. Third port of the first row is connected to the small switches in the next row, and those row is connected to the next row. By using this strategy, we can say that the input traffic would be sent easily and also the traffic enters to this strategy can shuffle during the sending information through different passes. We can shuffle this we can shuffle the packets enters into this structure. Okay. Maybe someone says that, okay, instead of having one switch fabric, may I have multiple switch fabric? We say yes. Look at this picture here in slide 27. There are lots of plants. We can say these plants here, we can use them in parallel. And each of those switch fabrics can handle only few amounts of data, each of them, but totally we will receive a strong power. Because they are working simultaneously in parallel. This strategy can be used in this strategy can support heavy amounts of traffic. So, for example, in Cisco CRS router, we are using this strategy, and it can receive a very high amount of outputs. Okay, just please wait a minute. Wait a minute. I will be back. Just wait, please. If I'm looking for higher speed transmission, I have to use interconnection network. For example, if you look on the switch fabric in CRS routers of Cisco, you can see that that router uses 8 different switching plans. Each of those switching plans has its own interconnection, which it has a 3-stage interconnection. 3-stage means that we have 3 levels of switches, something like this. This is a 3-stage. Look at this. Three-stage or 3 columns. The first stage, the second stage, and the third stage. Okay. So in Cisco CRS router, it uses 8 different switch plans. Each of them has a 3-stage interconnection network, and the switching capacity of this router is 100 terabits per second. 100 terabits per second. Okay, this router, just simply this router divide the traffic across those 8 different switch fabricates or switch plans. Okay. In the other side, we have an output port. Look at this. I will be back on this slide, okay? In the other side of our router, we have an output port. The output port, it's places after the switch fabric. Look at this slide here. This is input port, then switch fabric. The result will received into an output port. Okay. In the output port, firstly we have a queue. The received information should be put in a queue, and then you can see the link layer and line termination, layer 1 and layer 2 in networks. When we talked about queuing delay, we talked about this queue, the queue in the output port. The data should be stay in this queue before transmission. So here we need a buffering strategy, a drop policy, a strategy for congestion level situation, and scheduling disciplines. I should select the best packet among those packets standing in the queue. Okay, so we need scheduling discipline too. Totally, I can say I need buffer management strategies here, or queue management strategies here. Okay, but let me show something else. As I said, in a router we have 2 different strategies for putting a queue in the architecture of a router. The common approach is putting the queue in the output port. This is the common strategy. But some researchers, some people say that, okay, why you put buffer in the output ports? Put them in the input ports. Simply put those queues in the inputs. So some people say that I can put the queue in the inputs, and the others say that no, the best place is in output ports. If I put the queue in the input ports, I have an interesting problem. We call it head of line blocking, or HOL blocking. Look at this one here, in this example. You can see that the red packet should be forwarded into the, for example, the first output port. We have another red packet in the third input port. It should transfer into the first output port 2. They ask to send to move across the switch fabric, moving across the switch fabric to the same output ports. But I couldn't. I can't send 2 packets simultaneously to a similar output port. I should pass the switch fabric should pass them one by one. It cannot transfer them simultaneously. So at this case, one of those red packets should wait. The sending of the other packet should be finished, and then next red packet can be sent to the output port. But at this time, we have another packet, for example, a green packet here. The red packet stops because the output port is busy. Okay? The green packet should stop too, because the red packet is stopped. The green packet should be stopped. Because of the red packet. However, I can see that the green output port is free. Here we say that the packet in the head of the queue is blocked. So the rest of packets in the queue should stop too. We call it head of line blocking. The first packet blocks the rest packets. Here the green packet is blocked by the red one. However, its output port is free. So we called it head of line blocking. To solve this problem, we have to use virtual output queue or VOQ technology. In VOQ technology, instead of having one queue in the input, instead of having one buffer, we have n different buffers. N is number of output ports. One buffer for each of those output ports. So when one packet should be stopped because its output port is busy, the other packets shouldn't stop because they are free. Their output ports are free and they are standing in the right queue. One queue is blocked, but the other queues are not blocked. So they are in the right queue and they can move across the switch fabric easily without any blocking. Mostly when we use input port queuing in today's routers and switches, mostly when we are using input buffers, in the other side still we have used an output buffer too. Because it's very hard for the input ports to manage traffic of the output ports. So simply we send traffic to the output ports and we say, okay, if you have any problem, solve it yourself. It's not my problem. So we need a buffer in the output port. It should handle its problem itself. And we know that if a buffer becomes congested and became full, then queuing delay and queuing loss are trivial during the buffer over because of buffer overflow problem. When something happens, then a buffer flow happens. When does it happen? It happens when, for example, let's suppose that the speed of my input ports and output ports are, for example, 1 megabit per second. 1 megabit per second. At this time, what will happen if two or more than one input port send traffic to a specific output port? What will happen? It's completely clear. It would be overflow. We have different input ports who are sending their traffic to a specific output port. So the output port would be congested. It's trivial. It would be congested. And queuing delay and loss is something trivial. We can see something like this in the gateways of a network. In the gateway of a network, the gateway or the edge router should gather and integrate the whole traffic, and then the traffic would be sent through a special output port. So that port would be congested. How much we need? How much buffer we need? According to RFC 3439 rule of thumb, there is a rule of thumb. Let's suppose that in a typical RTT, for example, 250 millisecond, if the capacity of link is C, then the amount of buffer we need is something like this formula. RTT times in divided by root square of L. Okay? This is the amount of buffer that I need in the output port. It's a rule of thumb. It's not necessary, but it's a rule of thumb. Pay attention that if I increase the amount of buffer in an output port or in the network, it means that I increase the delays in the network. Adding more buffer means adding more delay to the network. So it's not an interesting item for us. However, we couldn't, we need some buffers too. Okay? Adding more delays means that Longer means that longer RTT. RTT is a parameter in TCP connections in layer 4 of the network. Okay. More delays means longer RTTs. So we need more capacity. According to this equation, we need more capacity. We cannot increase the amount of buffer in a router. If you look on a motherboard of a router, you can see that in that motherboard there is a lot of spaces have been used for buffers and memories. More buffer means more power consumption and more heat, so we need powerful cooling systems. And also we say that more buffers means more delays, so we cannot increase the buffers too many. Instead of that, we must use small buffers and manage those buffers carefully. That is enough for today. We will talk about buffer management strategies in the next session, inshallah. Is there any question? Okay. I wish the best for you in the rest of this network. Have a good time and goodbye.